Imagine staring into the night sky, not just at the twinkling stars we see from Earth, but far beyond, into the deepest, darkest corners of the cosmos. Out there, in the unimaginable vastness of space, titanic explosions are unfolding, so powerful they outshine entire galaxies for weeks. These are supernovas, the universe's grand farewell performances of dying stars. But among them, the most distant supernovas hold secrets so profound, they rewrite our understanding of time itself. Each one is a beacon from the edge of existence, a message sent billions of years ago, reaching us only now. What can these ancient cosmic fireworks teach us about the origins of everything? Supernovas aren't just spectacular light shows. They're the universe's way of recycling itself, scattering the very elements that make up planets, life, even you and me across the cosmos. Without them, the building blocks of everything we know wouldn't exist, but the supernovas that erupt at the farthest edges of the observable universe. They're something else entirely. Imagine catching a whisper from the dawn of time, a fleeting glimpse into the universe's fiery infancy. These distant explosions are time capsules, carrying clues about how the first stars lived, died, and shaped the cosmos we see today. Today, we're going on a journey to the very limits of what we can see and what we can comprehend. We'll unravel the mysteries of the universe's most distant supernovas, from the mind-bending physics that creates them to the cutting-edge technology that lets us witness their final, brilliant moments. Along the way, you'll discover how these cosmic giants help us measure the expansion of the universe, why some explode with the force of 100 billion suns, and what their light can tell us about the fate of everything. So brace yourself, we're about to dive into the most extreme, awe-inspiring, and mysterious explosions the cosmos has ever produced. The universe has been waiting billions of years to share these stories with us. Let's listen. At the heart of every supernova lies a star's dramatic, violent end, a cosmic finale so bright it can outshine an entire galaxy. Picture a star thousands of times larger than our sun running out of fuel. The delicate balance between gravity pulling inward and nuclear fusion pushing outward collapses in an instant. What happens next depends on the star's size and composition, but the result is always spectacular. For stars roughly 8 times more massive than our sun, the core implodes with such force that the outer layers rebound in a cataclysmic explosion, a type Roman II supernova. The shockwave blasts elements like carbon, oxygen, and iron into space, seeding future generations of stars and planets. But there's another kind, type Ia, where a dense white dwarf star steals material from a companion until it reaches a critical mass, triggering a runaway nuclear explosion so precise that astronomers use it as a standard candle to measure cosmic distances. These explosions aren't just about destruction, they're the universe's ultimate recyclers. Every atom in your body, the iron in your blood, the calcium in your bones, they were forged in the hearts of stars and scattered across space by supernovas. Without them, planets like Earth wouldn't have the heavy elements needed for life. But their importance goes even deeper. By studying the light from different supernova types, scientists can trace how the universe has expanded over billions of years. Type Ia explosions, with their predictable brightness, revealed the shocking truth that the cosmos isn't just expanding, it's accelerating, driven by a mysterious force we now call dark energy. So when we witness a supernova, we're not just watching a star die. We're uncovering the history of the universe itself, one explosive chapter at a time. Supernovas do more than just mark the death of a star. They serve as cosmic lighthouses, guiding astronomers through the unimaginable vastness of space. Think of them like mile markers on an endless cosmic highway. When a supernova erupts, its light travels across billions of light years, and by the time it reaches us, its brightness tells a story. Type Ia supernovas in particular are like cosmic rulers because they explode with a nearly identical peak brightness every time, scientists can compare how bright they appear from Earth to how bright they should be. That difference reveals just how far away they really are. It's like seeing a row of streetlights in the fog. Some appear dimmer because they're farther away, and that dimness tells you the distance. This technique led to one of the most startling discoveries in modern astronomy: dark energy. In the late 1990s, astronomers studying distant Type Ia supernovas expected to find the universe's expansion slowing down due to gravity. Instead, they found the opposite. The explosions were fainter than they should have been, meaning space itself was stretching faster over time. It was as if the universe had hit the gas pedal, accelerating its expansion in defiance of all predictions. That invisible force pushing galaxies apart, we still don't fully understand it, but we call it dark energy, and supernovas were the first to expose its existence. These stellar explosions don't just measure distance, they help map the universe's structure. Imagine plotting supernovas like pins on a three-dimensional cosmic map. Each one gives us a precise location, allowing scientists to trace the large-scale filaments and voids that make up the cosmos. Without them, we'd be navigating in the dark. Even more astonishing, some of the most distant supernovas we've observed erupted when the universe was less than half its current age. Their light has been traveling for so long that studying them is like flipping through an ancient cosmic photo album, revealing how the universe evolved over billions of years. So the next time you hear about astronomers calculating the distance to a far-off galaxy, remember it's often the flash of a dying star, billions of years old, that made it possible. Supernovas don't just illuminate the night sky, they illuminate the very fabric of reality, helping us decode the universe's deepest mysteries one explosion at a time. Among the countless supernovas observed over the decades, one stands out not just for its brilliance but for its staggering distance from Earth. Meet SN UDS10Wil, the most distant supernova ever recorded. This cosmic detonation occurred when the universe was just a toddler around 3.5 billion years old, and its light has traveled over 13.2 billion years to reach us. To put that into perspective, this explosion happened so long ago that Earth didn't even exist yet, and the Sun wouldn't form for another 9 billion years. How do we know just how far away this ancient explosion really is? The answer lies in a phenomenon called redshift. As light travels across the expanding universe, its wavelengths stretch, shifting toward the red end of the spectrum, like the Doppler effect for sound, but with light instead. The higher the redshift value, the farther and older the light source. SN UDS10Wil has a jaw-dropping redshift of 1.914. Meaning the light we see today left its source when the universe was only about a quarter of its current age. But redshift alone doesn't tell the full story. To confirm the distance, astronomers cross-reference this data with Type Ia supernova characteristics. Since these explosions always reach the same peak brightness, scientists could compare its observed brightness to its expected brightness, calculating just how much the light had dimmed over its 13 billion-year journey. It's like recognizing a lighthouse bulb from a known wattage. If it appears faint, you know it must be extremely far away. Discovering SN UDS10Wil wasn't just a record-breaking moment, it was a window into the universe's fiery youth. This explosion happened during the cosmic dawn, when the first generations of stars were seeding the universe with heavy elements. Studying its light gives us clues about the conditions of the early cosmos, from the density of matter to the rate of star formation back then. Every photon from this supernova is a messenger from a time when galaxies were just beginning to take shape, offering us a rare glimpse into the universe's most formative era. When we observe the light from SN UDS10Wil, we're not just looking across space, we're staring back in time. This supernova's light has been journeying through the cosmos for roughly 13.2 billion years. To grasp just how ancient that is, consider this. When this star exploded, the universe itself was only about 3.5 billion years old. that's younger than some of the oldest rocks on Earth today. The sheer scale of time involved is almost incomprehensible. If the entire history of the universe were compressed into a single year, this supernova would have flashed in early February, while our solar system wouldn't even form until September. This time delay isn't just a cosmic quirk, it's a fundamental feature of how we explore the universe. Light travels at a fixed speed, so the farther away an object is, the longer its light takes to reach us. By the time we detect a supernova like this one, the star itself has been gone for eons. Its explosion might have already seeded nearby space with elements that later formed planets, or even life, while we're only now seeing the first flicker of its death throes. It's like receiving a letter sent by someone who passed away generations ago, their words echoing across the centuries. What makes this particular supernova so extraordinary isn't just its distance, but what its age reveals about the early universe. Back then, the cosmos was a far more chaotic and violent place. Stars formed at breakneck speeds, lived fast and died young, scattering heavier elements into the void with each explosion. SN UDS10Wil's light carries fingerprints of that primordial era, allowing astronomers to study the chemical composition of the universe in its adolescence. The iron, silicon, and oxygen we find in its spectral signature weren't just forged in this one star. They were part of a growing legacy, the building blocks of everything that would come after. The age of this supernova also helps calibrate the cosmic timeline itself. By comparing its redshift with other ancient objects, scientists can piece together how quickly the universe was expanding back then. It's like finding a fossilized ripple in a stream. The size and shape tell you how fast the water was flowing when it was made. Each distant supernova adds another data point, helping us trace the universe's growth spurt from its fiery infancy to the vast, accelerating expanse we see today. So when we talk about 13-billion-year-old light, we're not just marveling at a number, we're uncovering the universe's childhood diary, one brilliant, fleeting entry at a time. Before Hubble, the distant universe was largely a blur. Then came this engineering marvel, orbiting above Earth's distorting atmosphere, its razor-sharp vision peeling back layers of cosmic history like never before. The Hubble Space Telescope didn't just observe distant supernovas, it revolutionized our ability to find them. Imagine trying to spot a single flickering candle in a city thousands of miles away, and you'll grasp the challenge Hubble tackles routinely. Its deep field surveys, where it stares at seemingly empty patches of sky for days, have revealed supernovas so faint they'd be invisible to any ground-based telescope. One of Hubble's greatest strengths is time, not just the time it spends collecting light, but the literal ages it lets us peer into. By combining its crystal-clear optics with patient observation, Hubble has captured supernovas erupting in galaxies so far away their light has traveled for over 12 billion years. These aren't just distant explosions, they're snapshots of the universe during its wild early years when galaxies were smaller, hotter, and far more volatile. Without Hubble's keen eye, these ancient stellar deaths would have remained hidden, their secrets lost in the cosmic background noise, but Hubble's role goes beyond discovery. It's also a master cosmic detective, dissecting the light from these supernovas to reveal their composition, energy, and even the conditions of the space they've traveled through. Every spectrum it takes is like a fingerprint, telling us not just about the explosion itself, but about the era it came from. When Hubble studies a supernova from 10 billion years ago, it's not just analyzing a star's death, it's sampling the primordial chemistry of the universe, back when heavy elements were still rare treasures scattered by the first generations of stars. Perhaps Hubble's most unexpected gift has been its ability to catch supernovas in the act, sometimes spotting them before they've even reached peak brightness. This real-time view lets astronomers watch these cosmic fireworks unfold across weeks or months, decoding the physics of the explosion as it happens. And because Hubble can revisit the same patches of sky year after year, It's built a decades-long album of cosmic change where a galaxy that looked quiet last year might suddenly blaze with the light of a dying star today. Without Hubble, our map of the universe's expansion would be riddled with gaps. Its precise measurements of distant supernovas helped pin down the rate of cosmic acceleration, cementing the case for dark energy. Every flicker it records from the edge of observable space isn't just data. It's a message in a bottle, tossed into the cosmic ocean billions of years ago, finally washing up on the shores of our curiosity. Hubble didn't just open a window to the distant universe, it handed us a telescope to read its oldest stories, written in the fading light of exploding stars. Spotting a supernova halfway across the universe is like trying to find a single spark in a forest fire while squinting through fog. The farther away these stellar explosions are, the fainter their light becomes, stretched thin across billions of light years. By the time it reaches us, that light is often drowned out by the glare of its own host galaxy or masked by interstellar dust. Even with today's most advanced telescopes, detecting these cosmic whispers requires patience, precision, and a bit of luck. One of the biggest hurdles is time. Unlike nearby supernovas, which might blaze brightly for weeks, distant ones flicker so faintly that their light can only be collected over months of continuous observation. Astronomers have to stare at the same patch of sky night after night, hoping to catch the subtle uptick in brightness that signals an explosion. It's a cosmic waiting game where the payoff might come years later or not at all. And even when they do spot a candidate, confirming it isn't easy. Other phenomena like flaring stars or distant quasars can masquerade as supernovas, sending researchers down frustrating dead ends. Then there's the interference. The universe is a crowded place, and light from distant supernovas has to travel through a gauntlet of obstacles, galaxies, nebulae, even the faint glow of cosmic dust that can scatter or absorb its signal. Imagine listening to a radio station while driving through a tunnel. The static and echoes make it hard to pick out the song. That's what astronomers face when analyzing light from these explosions. The data arrives fragmented, forcing scientists to piece together clues like detectives, reconstructing a crime scene from blurred security footage. But perhaps the most daunting challenge is sheer distance. The universe's expansion stretches the light from these supernovas, shifting it into the infrared spectrum, a wavelength range where Earth's atmosphere itself glows faintly, creating background noise that can obscure the signal. Ground-based telescopes have to fight this interference, while space telescopes like Hubble and JWST must rely on meticulous calibration to tease out the true brightness of these explosions. Every photon counts, and even the slightest miscalculation can skew measurements of the supernova's distance or energy. Despite these obstacles, the hunt continues because the rewards are too profound to ignore. Each distant supernova we detect is a time machine, offering a glimpse into the universe's youth. The challenges themselves become part of the story, pushing technology and human ingenuity to their limits. After all, the universe doesn't give up its secrets easily, but that's what makes uncovering them so extraordinary. Every distant supernova acts like a cosmic breadcrumb, marking a precise point in the vastness of space and time. But when you collect enough of these breadcrumbs, something extraordinary happens. They begin to trace the shape of the universe itself. Picture a surveyor plotting landmarks across an uncharted wilderness. Each supernova gives astronomers a fixed point to measure from, allowing them to construct intricate three-dimensional maps of the cosmos. These aren't just static snapshots, they reveal how the universe has stretched and evolved over billions of years. The key lies in those Type Ia supernovas we mentioned earlier. Because they explode with near-identical brightness, their observed luminosity tells us exactly how far away they are. Combine that distance with their redshift, how much their light has stretched due to cosmic expansion, and suddenly, every supernova becomes a data point in a grand cosmic graph. Plot enough of them and patterns emerge, vast filaments of galaxies, enormous voids where matter is scarce, and the subtle wrinkles left over from the universe's primordial infancy. It's like connecting dots in a coloring book, except the picture that emerges is the large-scale structure of reality. These supernova maps do more than just satisfy curiosity. They've become critical tools for measuring the universe's expansion rate, known as the Hubble constant. By comparing the distances of nearby supernovas with those at the edge of the observable universe, astronomers can track how expansion has changed over cosmic history. Think of it like measuring tree rings. The spacing between each ring tells you how fast the tree grew in a given year. Supernovas provide similar markers, showing us how quickly space was stretching at different epochs, revealing moments when dark energies' grip tightened or gravity briefly held sway. Some of the most ambitious astronomical projects, like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time, rely on supernovas as their guiding stars. These initiatives scan thousands of galaxies nightly, hunting for the telltale flare of distant explosions. Each new discovery sharpens our cosmic maps, filling in gaps like uncharted territories on an ancient explorer's parchment. And with technologies like the James Webb Space Telescope peering even deeper into the infrared, we're beginning to map regions so distant their light predates the formation of Earth itself. What's truly remarkable is how these maps keep surprising us. Early supernova surveys in the 1990s first hinted at dark energy's existence, but today's more precise measurements reveal subtle tensions in the data, hints that our understanding of cosmic expansion might still be incomplete. Some supernovas appear slightly brighter or dimmer than expected, suggesting pockets where the universe's expansion rate might vary. It's like discovering that your ruler changes length depending on where you measure, forcing scientists to question whether dark energy behaves differently across space or time. So the next time you see a star chart or a model of the universe, remember, those glowing points aren't just artistic flourishes. Many represent real supernovas, celestial signposts that have helped us sketch the contours of everything that exists. And with every new explosion we catalog, the map grows clearer, guiding us toward answers about the universe's ultimate fate. One brilliant flash at a time, these dying stars are drafting the atlas of the cosmos. The discovery of dark energy didn't come from a telescope's direct observation. It emerged from the faint, fading light of supernovas so distant their explosions predated the dinosaurs. In the late 1990s, two independent teams of astronomers were studying Type Ia supernovas, expecting to measure how much the universe's expansion was slowing due to gravity's relentless pull. Instead, they found something that defied all expectations. The universe wasn't just expanding, it was accelerating. The light from these ancient stellar explosions was dimmer than it should have been, implying they were farther away than anyone had predicted. It was as if the cosmos had a hidden engine pressing harder on the gas pedal with every passing moment. This revelation hinged on the predictable nature of Type Ia supernovas. Because they explode with nearly identical brightness, any deviation in their apparent luminosity could only mean one thing. The space between us and them had stretched more than our models accounted for. Imagine blowing up a balloon with dots on it. If the dots move apart faster than your breath can explain, something else must be inflating it. That something else is dark energy, an invisible force permeating all of space, driving galaxies apart at ever-increasing speeds. But how does dark energy actually work? Think of empty space not as a static void, but as a dynamic fabric with its own intrinsic energy. According to Einstein's theory of general relativity, space itself can possess a kind of anti-gravity, what he once called the cosmological constant. When the universe was younger and denser, gravity dominated, pulling matter together to form galaxies and clusters. But as expansion diluted matter's grip, dark energy's subtle push began to win out. By the time those distant supernovas erupted, dark energy was already subtly at work, and their light carries the fingerprints of that transition. What's astonishing is how recently we pieced this together. For most of astronomical history, the universe's fate seemed straightforward: expand forever but slow down. Dark energy flipped that narrative on its head. Now, the leading theory suggests dark energy makes up roughly 68% of the universe's total energy content, dwarfing both visible matter and dark matter. Yet, despite its overwhelming influence, we still don't know what it actually is. Is it a property of space itself, a new kind of field, or something even stranger? Supernovas remain our best tool for probing these questions. Each new distant explosion sharpens our measurements of dark energy's strength and consistency. Some theories suggest its effect might vary across time or space, subtle differences that only ultra-precise supernova observations could reveal. Future telescopes like the Nancy Grace Roman Space Telescope aim to discover thousands of these cosmic mile markers, mapping dark energy's influence with unprecedented detail. The irony is profound. The violent death throes of massive stars, visible across billions of light years, illuminate the universe's most mysterious, invisible force. Without supernovas, dark energy might still be lurking in the shadows, its existence unsuspected. Every time astronomers train their telescopes on another distant stellar explosion, they're not just studying a star's demise, they're decoding the hidden engine of the cosmos. The oldest supernovas in the universe tell a story written in elements that didn't even exist when the cosmos began. When we compare the chemical fingerprints of distant supernovas to those exploding in our cosmic backyard, the differences are staggering. Those early stellar explosions were cosmic pioneers, forging the first heavy elements in a universe that started with nothing but hydrogen, helium, and trace amounts of lithium. Take the remnants of a supernova from 10 billion years ago. Its spectrum shows far less iron, oxygen, or silicon than modern explosions. That's because the first generations of stars, called population 3 stars, formed from pristine gas untouched by previous stellar deaths. These giants burned hot and fast, fusing hydrogen into helium, then helium into carbon, but they rarely lived long enough to cook heavier elements like the iron that fills our blood or the calcium in our bones. When they exploded, they scattered these lighter elements like cosmic seeds, enriching the next wave of stars with slightly more complexity. Fast forward to today, and supernovas erupt in a universe already seasoned with heavy elements. Modern stars form from gas clouds laced with remnants of countless past explosions, so their cores cook elements far beyond what early stars could achieve. The supernova remnants we see nearby, like Cassiopeia A, are littered with sulfur, nickel, and titanium, elements that require multiple generations of stellar recycling. It's the difference between baking with only flour and water versus having a fully stocked pantry of ingredients. This metallicity gap isn't just trivia, it's a window into how stars evolve across cosmic time. The earliest supernovas were more energetic but chemically simpler, while modern ones, though sometimes less powerful, create a richer cocktail of elements. Some distant supernovas even show odd gaps in their spectra, missing elements like zinc or uranium, hinting that certain nuclear reactions hadn't yet become common in the universe's youth. But here's the twist: a few ancient supernovas defy expectations, showing unexpected spikes of heavy elements. These outliers suggest that even in the early universe, rare, monstrous stars could skip steps, forging gold or platinum in single, violent bursts. Finding these exceptions is like uncovering a medieval alchemist's notes, proof that under extreme conditions, the universe could accelerate its own chemical evolution. Every time astronomers analyze the light from a distant supernova, they're reading a recipe from the cosmic kitchen. The elements we find, or don't find, paint a picture of how stars lived and died in different eras, turning the universe from a barren landscape into the chemically rich tapestry we know today. Without those first, elemental supernovas, the periodic table would be empty, and so would we. The light from a distant supernova isn't just a signal from across space, it's a time capsule carrying snapshots of the universe's younger self. Imagine pressing play on a cosmic movie that's been running for billions of years, but you're only just now seeing the opening scenes. That's what happens every time astronomers detect one of these ancient explosions. Because light takes time to travel, the farther away a supernova is, the longer its light has been journeying to reach us. A supernova erupting 50 million light years away. We're seeing it as it looked 50 million years ago when Earth's dinosaurs were just beginning their reign. But the most distant ones, their light left when the universe was in diapers, and by the time it arrives here, the star itself has been dust for eons. This time delay isn't just a curiosity, it's our only way to peer into the universe's formative chapters. Think of it like receiving letters from a pen pal who lives years away by mail. Each message tells you what they were doing when they wrote it, not what they're up to now. Distant supernovas work the same way. Their light preserves conditions from the era they exploded, letting astronomers study how stars behaved when the cosmos was hotter, denser, and far more chaotic. The supernova SN UDS10Wil, for example, erupted when the universe was just 3.5 billion years old. Its light shows us a time when galaxies were smaller, collisions were more violent, and the first heavy elements were still being forged in the hearts of massive stars. What's even wilder is how this cosmic time travel affects our observations. A supernova's light doesn't just get dimmer with distance, it also stretches, shifting toward redder wavelengths as the universe expands. This redshift acts like a clock, telling us exactly how much the universe has grown since that light began its journey. A supernova with high redshift isn't just far away, it's a relic from an era when space itself was more compact. By comparing supernovas at different redshifts, astronomers can piece together a timeline of cosmic evolution, like flipping through pages of a photo album where each snapshot shows the universe a little older, a little more spread out. But here's the mind-bending part. Some of the most distant supernovas we've detected erupted in locations so far away that their light will never reach us again. The universe's expansion has carried those regions beyond our observable horizon, like ships disappearing over the curve of the ocean. The light we're seeing now is the last message we'll ever get from them, a final farewell from stars that vanished before Earth even existed. This time-stamped light does more than satisfy curiosity, it tests the laws of physics. Einstein's theory of relativity predicted that light from distant objects would stretch as space expands, but supernova observations let us measure that stretch with precision. Some ancient supernovas appear slightly brighter or dimmer than expected, hinting that the universe's expansion rate might have fluctuated over time. It's like finding wrinkles in the fabric of space-time itself, clues that our understanding of cosmic history might still be missing a few pages. So when astronomers point telescopes at these stellar explosions, they're not just cataloging cosmic disasters. They're reconstructing the universe's biography, one brilliant, fading chapter at a time. Every photon from a distant supernova is a whisper from the past, and together they tell the story of how we got here and where the cosmos might be headed next. Supernovas don't just destroy stars, they're the universe's ultimate alchemists, transforming simple atoms into the heavy elements that make up everything from planets to people. Deep in the heart of these explosions, temperatures soar to over 1 billion degrees, creating conditions so extreme that atomic nuclei smash together with enough force to overcome their natural repulsion. This process, called rapid neutron capture, or the R process, is how elements like gold, platinum, and uranium are born. Imagine a cosmic pressure cooker where ordinary iron nuclei are bombarded with so many neutrons that they bloat into heavier atoms in seconds, a stellar forge running at unimaginable intensities. But creating these elements is only half the story. A supernova's shockwave acts like a cosmic shotgun, blasting this newly forged material outward at speeds approaching 10% the speed of light. Gold atoms that might one day wind up in wedding rings or circuit boards begin their journey flung across light years of space, mixed with other heavy elements in an expanding cloud of stellar debris. Over millions of years, these particles become part of interstellar gas clouds, eventually collapsing into new generations of stars and planets. The iron in your blood, the calcium in your bones, even the trace amounts of gold in your smartphone. They all originated in the heart of a dying star billions of years ago. What's fascinating is how different supernova types contribute distinct elemental recipes to the cosmos. Core collapse supernovas from massive stars excel at producing lighter heavy elements like oxygen, neon, and magnesium, the building blocks of rocky planets. Meanwhile, the runaway nuclear explosions of Type Ia supernovas flood space with iron, nickel, and cobalt, explaining why these metals are so abundant in our solar system. But the rarest, most valuable elements require something even more extreme: neutron star collisions. When these ultra-dense stellar remnants spiral together and merge, they unleash a firestorm of neutron-rich material perfect for forging gold and platinum. One such collision might produce hundreds of Earth masses worth of precious metals in a single event. This stellar recycling program has been running since the first stars died, gradually enriching the universe with heavier elements over billions of years. Early supernovas from population Roman 3 stars, the universe's first stellar generation, spewed out mostly lightweight elements, while later explosions diversified the cosmic periodic table. Today, we can trace this chemical evolution by studying supernova remnants at different distances. Older remnants show simpler compositions, while younger ones contain the full spectrum of heavy elements, including those essential for life like phosphorus and iodine. Without supernovas scattering these ingredients across space, Earth would be a barren rock devoid of metal ores, fertile soil, or even the raw materials for DNA. Every heavy atom on our planet was manufactured in stellar furnaces and delivered via these titanic explosions. That means the device you're watching this on, the jewelry you might wear, even the neurons firing in your brain right now, they all owe their existence to stars that died before our sun was born. Supernovas aren't just endpoints in stellar life cycles. They're the universe's way of turning destruction into creation, ensuring that every star's death plants the seeds for new worlds and perhaps new life to emerge. Finding a supernova from the universe's first few billion years is like spotting a single lightning bug in a stadium filled with floodlights. Despite scanning thousands of galaxies and sifting through petabytes of telescopic data, astronomers have confirmed only a handful of these ultra-distant explosions, each one a needle in a cosmic haystack. Less than 50 supernovas with redshifts greater than 1 have ever been documented, and those with redshifts above 2, you could count them on one hand. This scarcity isn't just due to their mind-boggling distance. It's a consequence of time, technology, and the sheer physics of observing the edge of the observable universe. Part of the challenge stems from how briefly these explosions shine on cosmic timescales. A supernova might blaze brighter than its entire host galaxy for a few weeks, but over billions of light years, that flash gets stretched and diluted. By the time it reaches Earth, the light is often a billion times fainter than what our eyes can see, a flicker barely distinguishable from the glow of its home galaxy. Current telescopes have to stare at the same patch of sky for months, comparing thousands of images pixel by pixel, just to catch the subtle brightening that signals a potential supernova. Even then, most candidates turn out to be false alarms, distant quasars, flaring stars, or glitches in the data. Then there's the problem of cosmic dust. The early universe was a far grittier place, packed with dense clouds of primordial gas and dust that absorb and scatter light. A supernova's brilliance might be completely obscured by these interstellar curtains, its light transformed into heat before it ever reaches us. It's like trying to spot a lighthouse through a sandstorm. Even if the beam is powerful, the conditions might never let it shine through. but perhaps the biggest hurdle is sheer luck. Unlike nearby supernovas, which might erupt in any given galaxy once a century, these ancient explosions happened so long ago that catching one requires peering back to an era when galaxies themselves were still taking shape. The odds of a star exploding at just the right moment, in just the right orientation, with its light reaching us now after billions of years in transit. They're astronomically low. Each confirmed distant supernova represents not just scientific effort, but cosmic serendipity. That's why every new discovery sends ripples through the astronomy community. When a team confirmed supernova SN 1620F in 2016, a relic from when the universe was 2.7 billion years old, it made headlines not just for its distance, but for what its unusual brightness suggested about early stellar chemistry. Another breakthrough came in 2022 when the James Webb Space Telescope spotted a supernova candidate at redshift 3, potentially tripling the previous record holder's age. These aren't just data points, they're Rosetta Stones, helping decode how the first stars lived and died, and how the infant universe differed from the cosmos we know today. The rarity of these events also makes them priceless calibration tools. Each one helps refine our models of cosmic expansion, testing whether dark energy's influence has changed over time. Finding even a few more could settle a simmering debate. Is the universe's acceleration constant, or does it fluctuate? Every flicker from the edge of existence brings us closer to answers. So when astronomers celebrate the discovery of a single supernova halfway across the observable universe, they're not just marking another entry in a catalogue. They're holding a piece of cosmic history, a fleeting glimpse into an era when the universe was young, wild, and utterly unlike anything we see around us today. Each one is a triumph of patience, technology, and the relentless human drive to explore what lies beyond the limits of vision. Einstein predicted it over a century ago. Massive objects warp the fabric of space-time so profoundly that they bend light itself. Today, astronomers use this phenomenon, called gravitational lensing, to spot supernovas so distant they'd otherwise be invisible. Picture a magnifying glass floating in space, but instead of glass, it's an entire galaxy cluster with the mass of 1,000 trillion suns. When light from a faraway supernova passes near this cosmic lens, it gets stretched and amplified, sometimes by factors of 50 or more. It's like nature handing us a free telescope, letting us peer deeper into the universe than our technology alone could ever achieve. One of the most dramatic examples is supernova Rifstal, spotted in 2015. This explosion happened 9.3 billion years ago, but its light took multiple paths around a massive galaxy cluster, creating 5 separate images arranged in a cosmic cross. Like a celestial hall of mirrors, each image showed the supernova at slightly different stages of its explosion, giving astronomers a time lapse of stellar death from multiple angles. Normally, we'd only catch a supernova at one moment in its life cycle, but thanks to lensing, Rifstal played out in staggered snapshots across weeks, offering unprecedented insights into how these explosions evolve. But lensing does more than just magnify, it distorts. Some lensed supernovas appear as smeared arcs or bizarre rings, their light warped into shapes that defy ordinary physics. The supernova nicknamed SN Requiem appeared as 3 mirrored images in 2016, but astronomers predict it'll reappear elsewhere in the same galaxy cluster around 2037. That's because the light took different routes around the lensing mass, some paths longer than others, delivering the same explosion to Earth decades apart. It's as if the universe hit pause, then rewind on a cosmic blockbuster. These Einsteinian quirks aren't just curiosities, they're essential tools. Without lensing, supernovas like SN Zwicky, shining from when the universe was just 2 billion years old, would be too faint for even our best telescopes. But when a foreground galaxy cluster bends and focuses that ancient light, suddenly details emerge. The supernova's chemical composition, the structure of its host galaxy, even the distribution of invisible dark matter in the lens itself. Every lensed supernova is a 2-for-1 deal, revealing secrets about both the distant explosion and the cosmic lens magnifying it. Perhaps the most astonishing aspect is how lensing turns the universe into a natural laboratory. The same physics that lets us detect these far-flung supernovas also lets us test general relativity on scales Einstein never imagined. When light from a supernova curves around a galaxy cluster, the amount it bends reveals the cluster's total mass, including the dark matter we can't see. It's like weighing an invisible object by watching how it bends a beam of light. Gravitational lensing doesn't just help us find distant supernovas, it transforms them into cosmic messengers, carrying encoded details about the structure of space-time itself. Every warped image, every delayed reappearance, every magnified flicker is a puzzle piece in our understanding of how mass shapes the universe. And as telescopes grow more powerful, we'll likely find even more of these cosmic mirages, each one bending the rules of physics to bring the universe's most remote fireworks into view. Right now, as you watch this, engineers and astronomers are building the next generation of cosmic time machines, telescopes so powerful they'll spot supernovas from the universe's first billion years. The James Webb Space Telescope is just the beginning. With its infrared eyes, JWST can peer through the dust that obscures ancient stellar explosions, catching light so red-shifted it's invisible to other observatories. But what comes next will push the boundaries even further. Projects like the Nancy Grace Roman Space Telescope, set to launch in the next few years, will scan vast swaths of sky with a field of view 100 times wider than Hubble's. Imagine finding not just 1 or 2 distant supernovas per year, but hundreds, each one a pinprick of light holding secrets about the cosmos' earliest epochs. These new telescopes don't just see farther, they see smarter. Take the Vera-C, Rubin Observatory's legacy survey of space and time, which will photograph the entire southern sky every few nights for a decade. Its 32 billion pixel camera won't just spot distant supernovas, it'll catch them in their earliest moments, sometimes before they even reach peak brightness. This real-time view lets astronomers watch these explosions unfold hour by hour, like rewinding a cosmic film to study the exact moment a star's core collapses. And because Rubin will scan so frequently, it could discover supernovas in regions of space we've never monitored before, perhaps revealing entirely new types of stellar deaths lurking in the universe's distant past. But the true game-changer might be what comes after Webb and Roman. Concept telescopes like LUVOIR, a proposed space observatory with a mirror 15 meters across, could detect supernovas so ancient they erupted before galaxies fully formed. Its staggering light-gathering power would analyze chemical fingerprints in these explosions with precision we can barely imagine today. We're not just talking about spotting more supernovas, we're talking about reading their light like a detailed biography, uncovering the temperature, density, and even the magnetic fields present during the universe's first stellar generations. The hunt for these primordial supernovas isn't just about breaking records, it's about filling in the missing chapters of cosmic history. Every new telescope brings us closer to answering fundamental questions. How did the first stars differ from those we see today? Did early supernovas explode differently in the denser, hotter universe? And crucially, could their unique conditions have forged elements in ways modern stars no longer can? Each discovery has the potential to rewrite our understanding of stellar evolution, dark energy's early influence, and the chemical enrichment of the cosmos. What makes this era particularly thrilling is how these telescopes will work together. JWST's detailed infrared spectra might identify a candidate from the cosmic dawn. Then Roman could track its light curve for months, while ground-based observatories like the extremely large telescope measure its redshift with unprecedented accuracy. It's a tag-team approach to cosmic detective work, with each instrument contributing a piece of the puzzle. Together, they'll build a three-dimensional map of supernovas across time and space, revealing patterns we can't yet see from today's limited samples. We're standing on the brink of a revolution in how we study the universe's most violent and most creative events. Within the next decade, the number of known ancient supernovas could multiply from a handful to thousands, giving us statistical power to test theories that were pure speculation just years ago. The light from these explosions has been traveling for over 90% of the universe's lifetime, and soon our technology will finally be ready to receive their messages in full. When that happens, we won't just be observing the past, we'll be rewriting the story of cosmic beginnings. If a supernova could scream, it would shatter planets. While sound can't travel through the vacuum of space, the sheer scale of these explosions defies imagination. So let's translate that fury into terms our ears might understand. Picture every instrument in Earth's largest orchestra playing their loudest notes simultaneously. Now multiply that volume by 100 trillion. The energy released in a single supernova outshines an entire galaxy for weeks, equivalent to detonating octillions of nuclear bombs in an instant. Convert that energy into sound waves, and you'd have a cosmic chord vibrating at frequencies beyond human hearing, a deep, bone-rattling bass note lasting months as the shockwaves ripple outward. But raw volume isn't the most terrifying part, it's the texture. A supernova's sound would layer collapsing star cores like collapsing skyscrapers, nuclear fusion chain reactions resembling machine gun fire, and the hiss of neutrinos, trillions of these ghostly particles blasting through matter as effortlessly as radio waves through walls. The closest earthly comparison might be standing next to a volcanic eruption while every lightning strike on Earth hits at once, wrapped in the metallic shriek of tearing steel. Even then, we're only grasping at shadows. The true cacophony would include frequencies so low they'd vibrate continents, and so high they'd ionize the air. NASA scientists actually attempted this thought experiment using data from Cassiopeia, a supernova remnant. By translating different wavelengths of light into corresponding sound pitches, X-rays as sharp clicks, infrared as deep hums, they created an eerie symphony of stellar death. The result, a building crescendo of metallic rings and thunderous booms, mirroring how shockwaves fragmented the dying star's layers. It's not real sound, but it reveals something profound. Supernovas have rhythm. Their light curves pulse like a heartbeat, with brightness spikes corresponding to different stages of the explosion. You're hearing the death throes of a star translated into the language of vibration. Perhaps the strangest auditory illusion comes from gravitational waves, ripples in spacetime detected when massive objects collide. The merger of two neutron stars in 2017 produced waves that, when sped up, sounded like a cosmic chirp. Apply that principle to a supernova's collapsing core, and you might hear space itself ringing like a struck bell, with frequencies revealing the star's mass and spin. It's a reminder that the universe communicates through more than just light. We're learning to listen to its hidden frequencies. So while space remains silent to our ears, the next time you see a supernova image, imagine the roar trapped inside that brilliance, an orchestra of destruction where every instrument is a force of nature, playing the final, irreversible note of a star's life. It's a song written in shockwaves and neutrinos, one we're only beginning to decode. These distant supernovas aren't just relics of the past, they're cosmic crystal balls offering glimpses into how the universe itself might end. Every time astronomers measure a supernova's distance and brightness, they're not just studying a star's death, they're adding another day to point to the grandest question of all: what fate awaits everything that exists? Take the concept of heat death, the idea that the universe will gradually cool into darkness as expansion disperses energy beyond recovery. Distant supernovas provide critical evidence for this theory. The way their light dims over billions of light years confirms space is stretching at an accelerating rate, with dark energy acting like an unstoppable force pushing galaxies apart. Eventually, this expansion could leave every star system isolated in an ever-growing void, their light stretched into invisibility. Supernovas like SN UDS10Wil show us this process in action, revealing how much faster space stretched in the past compared to today. It's like watching the first domino fall in a chain reaction that won't finish for trillions of years. But heat death isn't the only possibility. Some models suggest dark energy might grow stronger over time, leading to a far more violent finale, the Big Rip. In this scenario, the accelerating expansion doesn't just isolate galaxies, it tears apart everything down to atoms themselves. Distant supernovas help test this idea too. By comparing explosions from different cosmic eras, astronomers look for subtle changes in how quickly expansion accelerates. If dark energy's push is getting stronger, supernovas at the universe's edge should appear slightly fainter than current models predict. It's like noticing a car's cruise control isn't just maintaining speed but silently pressing harder on the gas. Then there's the cyclical model, the poetic idea that the universe might collapse back on itself in a big crunch, only to rebound in a new Big Bang. While most distant supernovas support endless expansion, a few outliers show peculiar brightness patterns that keep this theory alive. Some ancient explosions appear slightly brighter than expected, hinting that gravity may have temporarily slowed expansion in the universe's youth. It's a long shot, but if future telescopes find more of these anomalies, they could rewrite our cosmic expiration date. What makes supernovas indispensable to these theories is their role as cosmic mile markers. Just as highway signs tell you how far you've traveled, supernovas measure how much space has stretched over eons. Their light carries imprints of every warp and ripple it crossed, letting scientists reconstruct the universe's expansion history like detectives piecing together a timeline from scattered clues. But here's the twist. Some theories suggest dark energy isn't constant, it might fluctuate or even reverse someday. A supernova exploding right now in a galaxy 40 billion light-years away could carry evidence of such a shift, but its light will never reach us because space is expanding faster than light can traverse it. It's a humbling reminder that even our best cosmic maps have horizons we can't see beyond. Whether the universe ends in ice, fire, or rebirth, distant supernovas are the flickering beacons guiding us toward answers. Every explosion we observe adds another piece to the puzzle, not just of how stars die, but of how everything might one day end. And long after the last supernova fades from view, their legacy will linger in the atoms they forged, the mysteries they helped unravel, and the profound truth they've shown us. To study the death of stars is to glimpse the destiny of the cosmos itself. Long before galaxies spiraled into existence, long before planets coalesced from cosmic dust, the universe's first star's population 3 ignited in the darkness. These primordial giants bore little resemblance to the stars we know today. Born from pure hydrogen and helium, untouched by the heavy elements that fill modern stars, they burned hotter, faster, and more violently than anything that would follow. When their time came to explode, their supernovas weren't just stellar deaths, they were cosmic firsts, forging the very foundations of everything to come. Picture a star hundreds of times more massive than our Sun, its core temperatures soaring beyond 100 million degrees, without elements like carbon or oxygen to help regulate nuclear reactions. These behemoths fused hydrogen at breakneck speeds, living mere millions of years instead of billions. Their deaths were equally extreme. When a population 3 star collapsed, it didn't just explode, it likely disintegrated in a pair instability supernova, a runaway thermonuclear detonation so powerful it left no black hole behind. The entire star would have vaporized in a blast visible across the universe, scattering its raw elemental guts into the void. This wasn't recycling, it was the universe's first act of creation, transforming primordial gas into the seeds of complexity. But here's what makes these ancient explosions truly alien: their chemistry. modern supernovas spew iron, nickel, and silicon elements forged in their cores over millennia. Population 3 supernovas, by contrast, produced almost none of these heavy metals. Instead, they flooded space with lighter elements like carbon, oxygen, and nitrogen, the building blocks of future stars and planets. Some theorists even suggest these early supernovas created bizarre, short-lived elements impossible in today's stellar environments, substances that vanished as soon as they formed, leaving no trace except in mathematical models. Their violence also shaped the cosmos in ways we're only beginning to understand. A single population 3 supernova could have sterilized entire swaths of the early universe, its ultraviolet radiation boiling away nearby gas clouds before new stars could form. Yet those same explosions might have triggered star birth elsewhere, their shockwaves compressing distant pockets of gas until they ignited. It's a paradox. These supernovas were both destroyers and midwives, clearing space while simultaneously planting the seeds for everything that followed. The most tantalizing question remains: could any of these first-generation stars have survived to the present day? A handful of theorists speculate that a few population 3 stars might still linger in the universe's quietest corners, too small to have exploded, hiding in plain sight among younger stars. Finding one would be like discovering a living dinosaur, a relic from the universe's fiery dawn, holding secrets about how it all began. For now, all we have are traces, whispers in the light of quasars, odd chemical signatures in ancient gas clouds. But with telescopes like JWST peering deeper than ever, we might soon catch the ghostly afterglow of these primordial explosions, their light stretched into infrared by 13 billion years of cosmic expansion. Every flicker we detect won't just be a supernova, it'll be a message from the universe's first moments, written in the ashes of the stars that made everything else possible. Long before telescopes or modern astronomy, humans looked up at the night sky and witnessed celestial miracles, supernovas blazing so brightly they outshone every other star. One of the most famous occurred in the summer of 1054, when Chinese astronomers recorded a guest star in the constellation Taurus so vivid it was visible even during daylight for 23 days. This was the birth of the Crab Nebula, a supernova remnant we still study today. But imagine if those same ancient stargazers had peered into the abyss and seen the distant supernovas we now detect, explosions so far away their light is 1 billion times fainter than the dimmest visible star. The contrast between what our ancestors witnessed and what we now know paints a striking picture of how much the cosmos has revealed to us and how much remains hidden. The supernova of 1054 wasn't an isolated event. Across centuries and continents, civilizations documented these sudden celestial visitors. Korean astronomers called them forked stars, while European monks described them as divine signs. The supernova of 106 even left its mark in petroglyphs by Native American cultures, etched into rock as a crescent moon beside an 8-pointed star. What made these explosions so unforgettable was their immediacy, a star where none had been before, blazing with impossible intensity before fading over weeks or months. People didn't need technology to see them. The spectacle was written across the sky in letters of fire. Now fast forward to today. With the naked eye, you'd never know that right now, somewhere in the depths of space, a supernova from the universe's first few billion years is flickering into view. Its light may have traveled for 12 billion years, but by the time it reaches Earth, it's diluted to a whisper, detectable only by the most sensitive instruments. The difference between these ancient recorded supernovas and the ones we study now isn't just about brightness, it's about time. Those historical explosions were close enough that their light reached us within human lifetimes, while the most distant ones are cosmic time capsules, their stories only now arriving after epochs of travel. Yet in a way, those early observers had an advantage we lack: the raw, visceral impact of witnessing a star's death firsthand. There's something humbling about imagining a farmer in medieval China pausing in the fields, staring slack-jawed at a new star brighter than Venus. Today, we analyze supernovas through graphs and spectra, their brilliance reduced to pixels on a screen. We've traded awe for understanding, and while the trade is worthwhile, it's worth remembering that the universe once spoke to humanity in a language of sudden, shocking light. The Crab Nebula supernova wasn't just a spectacle, it changed astronomy. Its remnant became a Rosetta Stone for modern astrophysics, helping us decode how supernovas enrich the cosmos with heavy elements. But the distant supernovas we detect today, they're rewriting the textbooks entirely. While our ancestors marveled at temporary stars, we're unraveling the life cycles of the first stellar generations, measuring the expansion of spacetime itself, and peering into eras when the universe was young and wild. The night sky hasn't changed, but our ability to listen to its oldest stories has grown beyond anything those ancient astronomers could have dreamed. The numbers behind distant supernovas are so staggering they defy earthly comparisons, but let's try anyway. When one of these cosmic titans explodes, it unleashes more energy in seconds than our sun will produce over its entire 10-billion-year lifetime. That's not hyperbole. A typical core collapse supernova releases around 10 to the 44 joules of energy. Picture every nuclear weapon ever built detonating simultaneously, then multiplying that blast by 10 billion. You're still not close. The sun, by contrast, radiates a modest 10 to the 26 watts, meaning a single supernova outshines it by a factor of 100 billion during its peak brightness. It's like comparing a birthday candle to the surface of a star. But raw power isn't the only mind-bending aspect, it's the efficiency. These explosions convert matter into energy with terrifying precision. When a massive star's core collapses, up to 10% of its mass transforms directly into energy via Einstein's famous E=mc². For a star 20 times more massive than our Sun, that means nearly 2 octillion tons of material. Roughly the mass of 5,000 Earths vanishes in an instant, reborn as pure radiation. The shockwave alone accelerates particles to 99.9% light speed, creating cosmic rays that can cross entire galaxies. Even our most powerful particle accelerators can't match this natural violence. To grasp what this means on a cosmic scale, consider the solar system's most explosive events. The Carrington event of 1859, the largest solar storm ever recorded, unleashed energy equivalent to 10 billion atomic bombs, enough to fry telegraph systems worldwide. A distant supernova delivers that same punch every nanosecond for weeks. The eruption that created the Crab Nebula in 1054 was so intense its gamma rays would have sterilized any nearby planets. Yet compared to some of the hypernovas we've detected from the early universe, even that cataclysm pales. Certain primordial explosions may have been 100 times more energetic, their shockwaves carving bubbles in the intergalactic medium visible billions of years later. Human attempts to harness such power seem laughably quaint. The Tsar Bomba, history's largest nuclear test, yielded 58 megatons, enough to shake continents. Stack 50 million of those detonations together, and you'd match just 1 second of a supernova's output. Even our wildest theoretical weapons, planet-cracking antimatter bombs or hypothetical quark nova triggers, couldn't scratch the surface of this stellar fury. The universe operates on a scale where energy is measured not in bombs or reactors, but in stars converted to light. Yet for all their destructive potential, these explosions are cosmic creators. The energy they release isn't wasted, it's the universe's ultimate recycling program. That unimaginable blast cooks raw hydrogen and helium into heavier elements, then catapults them across interstellar space at millions of miles per hour. Every gold atom in your jewelry, every calcium ion in your bones was forged in this stellar inferno and delivered by its shockwaves. The same energy that could vaporize solar systems also built them, turning destruction into the raw materials for new worlds. So while we can't truly comprehend these numbers, we're walking proof of their creative power, the universe turning its most violent moments into the building blocks of life itself. When a supernova's fury finally subsides, the real cosmic drama is just beginning. The stellar corpse left behind isn't some lifeless husk, it's one of the most extreme objects in the universe, packing the mass of an entire star into a space smaller than a city. For stars between about 8 and 20 times the mass of our Sun, the core collapse typically forms a neutron star, where matter gets crushed so densely that a single teaspoonful would weigh billions of tons on Earth. Picture Mount Everest compressed into a sugar cube, with a magnetic field a trillion times stronger than our planet's and a surface so smooth that if it were the size of Manhattan, its tallest imperfections would be no thicker than a sheet of paper. These spinning powerhouses often reveal themselves as pulsars, beaming radiation across space with metronome precision. Some rotate hundreds of times per second, their lighthouse-like flashes visible from millions of light years away. But when even neutron stars can't contain the leftovers, the result is far more ominous. For the most massive progenitor stars, those tipping the scales at 20 solar masses or more, the core collapse bypasses neutron star formation entirely, instead creating a black hole. This isn't the sci-fi version with a visible swirling disk you could admire from a safe distance. Initially, it's an invisible point of infinite density wrapped in an event horizon smaller than a grapefruit, so dense that light itself can't escape its grasp. Yet, given cosmic timescales, these newborns grow into monsters. Over millions of years, they vacuum up surrounding gas, dust, and even other stars, their event horizons expanding as they feast. Some eventually become the supermassive black holes anchoring galaxies, the same behemoths we now detect devouring matter in distant quasars. Between these extremes lie stranger fates. Occasionally, a supernova's collapse forms a magnetar, a neutron star on steroids, with magnetic fields so intense they could strip the data from every credit card on Earth halfway across the Milky Way. Others might birth exotic hybrid objects like quark stars, where neutrons themselves dissolve into their fundamental components under pressures too extreme for normal matter to withstand. And in rare cases, the explosion might be so violent it leaves nothing behind at all. A phenomenon called unbound supernovas, where the star completely disintegrates, scattering its guts across space without even a black hole or neutron star as a tombstone. The evolution of these remnants tells its own extraordinary story. A young neutron star starts out blazing at millions of degrees, cooling over millennia as its trapped heat slowly leaks into space. Some develop accretion disks from leftover stellar material, becoming X-ray binaries that flare unpredictably as they digest their stolen meals. Others wander alone through the galaxy, their surfaces gradually solidifying into crystalline crusts under unimaginable pressures. Black holes, by contrast, are far hungrier neighbors. Given enough time near dense gas clouds or unfortunate companion stars, they can grow from stellar mass leftovers into intermediate or even supermassive monsters, their gravitational influence reshaping entire galaxies around them. Perhaps most remarkably, these remnants become the universe's ultimate recyclers. The supernova's initial blast disperses heavy elements into interstellar space, while neutron stars and black holes continue the process over billions of years. Neutron star collisions detected through both gravitational waves and brilliant kilonova explosions are cosmic gold mines, quite literally. A single merger can forge hundreds of Earth masses worth of platinum, gold, and other precious metals in seconds. Black holes, meanwhile, indirectly encourage star formation by compressing nearby gas with their gravity, sparking new stellar nurseries even as they consume matter themselves. So when we look at the Crab Nebula's pulsing heart or detect X-rays from Cygnus X1's invisible companion, we're not seeing endpoints, we're witnessing the next chapter in a star's life cycle. These remnants are the universe's way of turning destruction into new possibilities, ensuring that even in death, stars continue shaping the cosmos in ways we're only beginning to understand. Supernovas embody the ultimate cosmic paradox. They're both life's greatest threat and its essential architect. For any planet orbiting a star within 30 light years of one of these explosions, the aftermath would be apocalyptic. The initial gamma ray burst alone carries enough energy to strip away ozone layers like tissue paper, bathing surfaces in lethal ultraviolet radiation. X-rays and cosmic particles would follow, smashing into atmospheres at near light speed, turning fertile worlds into radioactive wastelands. Some theories suggest Earth may have suffered minor extinction events from distant supernovas in its past, with traces of iron-60 isotopes, a radioactive fingerprint of stellar explosions found deep in ocean sediments and lunar regolith. It's a sobering thought. Life as we know it exists only because no nearby star has died violently during humanity's brief existence. Yet the same explosions that could sterilize worlds also make life possible. Every carbon atom in your DNA, every oxygen molecule you breathe, every speck of calcium in your bones was forged in a star's core and scattered by supernova shockwaves. These stellar death throes are the universe's primary distribution network for heavy elements, catapulting them across interstellar space at millions of miles per hour. When our solar system formed 4.6 billion years ago, it condensed from a gas cloud enriched by generations of these explosions, a celestial inheritance that turned Earth into a life-bearing oasis. The iron in our blood recycled supernova debris, the gold in our jewelry cast into the void during neutron-star collisions triggered by ancient stellar deaths. Even elements like phosphorus, crucial for cell membranes and energy transfer, are disproportionately abundant in life's chemistry because supernovas produce them in staggering quantities. This duality extends to the cosmic scale. While a nearby supernova could reset a planet's evolutionary clock, the same explosions might also kickstart life elsewhere. Shockwaves from stellar deaths compress nearby gas clouds, triggering new star formation, and with it, new planetary systems. Recent studies of meteorites reveal they contain prebiotic molecules like amino acids, suggesting supernova debris might carry not just raw elements but potential building blocks for life. There's even a controversial hypothesis called panspermia, proposing that microbial life could hitch interstellar rides on debris ejected by supernovas, seeding galaxies like dandelions scattering seeds. Whether this is possible remains hotly debated, but the underlying principle holds. These explosions don't just destroy, they disperse, enrich, and potentially even transport life's ingredients. The search for extraterrestrial life must grapple with this balancing act. Astronomers scanning exoplanet atmospheres for biosignatures prioritize systems far from recent supernovas, where life would have had time to recover and flourish. But they also focus on stars with the right metallicity, enough heavy elements from past supernovas to form rocky planets, yet not so many that radiation from subsequent explosions would overwhelm planetary defenses. It's a Goldilocks scenario on a galactic scale. The most promising worlds might orbit stars born from the ashes of supernovas that exploded just early enough to deliver life's raw materials, but not so recently as to sterilize the neighborhood. This delicate interplay between destruction and creation reveals a deeper truth about the cosmos. Life isn't separate from stellar violence, it's a direct consequence of it. The same forces that could wipe us out also built us, atom by atom. As we scan the universe for other living worlds, we're not just looking for Earth-like planets. We're searching for places where supernovas struck the perfect balance, close enough to matter, but not so close as to erase the future. When a distant supernova erupts, its light doesn't reach us unchanged. It carries the fingerprints of an expanding universe. The phenomenon known as redshift stretches the light's wavelength during its billion-year journey, transforming what might have been brilliant blue or white into deep crimson hues by the time it arrives in our telescopes. This isn't just a visual quirk, it's a fundamental clue about the cosmos's structure and history, written in the very color of dying stars. To understand why this happens, picture a cosmic rubber sheet, the fabric of space-time itself. As the universe expands, it stretches light waves traveling through it, much like drawing out a slinky and watching its coils widen. A supernova's light, emitted as ultraviolet or visible wavelengths, gets pulled toward the red end of the spectrum over eons of travel. The farther the light journeys, the more extreme this stretching becomes. A supernova with a redshift of 1, for example, means its light has doubled in wavelength by the time it reaches us, turning what was once violet light into infrared, invisible to human eyes without technological aid. Astronomers don't just observe this reddening, they decode it. By analyzing a supernova's spectrum, the unique fingerprint of light split into its component colors, scientists can measure exactly how much the light has stretched. This redshift value becomes a cosmic yardstick, revealing not only the explosion's distance but also how fast the universe was expanding when the star died. It's like listening to a train whistle. As the train moves away, the pitch drops, and from that change you can calculate its speed. Supernova light does the same, with redshift serving as the universe's Doppler effect. But here's where it gets even more fascinating. To compare supernovas across cosmic time, astronomers must correct for redshift, essentially reverse engineering the light to how it would have appeared at the moment of explosion. This involves sophisticated mathematical models and calibration against known supernova templates. Imagine receiving a letter written in ink that's faded over centuries. Redshift correction is like restoring the original vibrant color, allowing us to read the message as it was first written. Without this step, a supernova from 10 billion years ago might appear misleadingly dim or cool, skewing our measurements of cosmic distances and expansion rates. The James Webb Space Telescope has revolutionized this process by observing in infrared, where highly redshifted light becomes visible. Where Hubble might see only a faint red smudge, Webb detects intricate spectral lines, letting astronomers reconstruct the supernova's true properties. This is crucial because certain supernova types, like type Ia, have consistent peak brightness but only after accounting for redshift. A supernova that looks dim might either be far away or shrouded in dust. Redshift measurements help distinguish between the two, ensuring our cosmic maps stay accurate. Redshift isn't just a technical hurdle, it's a time machine. The light from SN UDS10Wil, redshifted to infrared, tells us not just where the explosion happened, but when. A snapshot of the universe at 3.5 billion years old, when galaxies were smaller and the cosmos was denser. Every crimson-hued photon is a piece of that era, preserved against the stretching of space itself. And as we refine our ability to untangle these stretched wavelengths, we're not just observing the past, we're learning to read the universe's diary, written in the shifting palette of dying stars. While professional astronomers command massive telescopes and supercomputers, some of the most exciting supernova discoveries start with a backyard telescope and a sharp-eyed amateur. Across the globe, citizen scientists regularly contribute to finding these stellar explosions, sometimes even spotting them before major observatories do. Take the story of Tom Bowles, a retired engineer in England who manually checked telescope images night after night, eventually discovering over 150 supernovas from his modest setup. Or the Australian amateur Robert Evans, who holds the record for visual supernova detections, 42 confirmed finds using nothing but his memory of galaxy patterns and a homemade telescope. These aren't isolated cases. Modern sky surveys now specifically invite amateur astronomers to sift through real-time data, turning their passion into critical scientific contributions. The process works like a cosmic neighborhood watch. Automated telescopes scan thousands of galaxies nightly, but algorithms often miss subtle brightening, especially in distant galaxies where supernovas appear as faint specks. That's where human pattern recognition excels. Platforms like the Zwicky Transient Facility and the All-Sky Automated Survey for Supernovas stream images to volunteers who flag anything unusual. In 2022 alone, amateurs helped identify 17% of all known supernovas, including several from galaxies over 500 million light-years away. Some discoveries have even reshaped professional research, like Supernova 2014J in the galaxy M82, which amateurs spotted early enough for telescopes worldwide to capture its critical first hours, data that revealed never-before-seen details about Type Ia explosions. What makes these contributions remarkable isn't just the volume, but the accessibility. High-end amateur equipment today rivals professional setups from the 1990s, with 14-inch telescopes and cooled CCD cameras capable of capturing galaxies halfway across the observable universe. Online tools like the American Association of Variable Star Observers Supernova Search Interface let anyone compare recent images to archival shots, hunting for that telltale new point of light. Even smartphone apps now notify users when a galaxy of interest enters their local observing window, turning a casual stargazing session into a potential discovery opportunity. Perhaps the most heartwarming aspect is how these discoveries bridge generations. The Supernova Seekers project in Japan pairs retired engineers with schoolchildren, teaching them to analyze telescope data together. In 2021, their combined efforts detected a supernova in the galaxy NGC 7814, a find celebrated as much for its scientific value as for its intergenerational collaboration. Similarly, the Galaxy Zoo citizen science platform has involved over 500,000 volunteers in classifying galaxies, with dozens stumbling upon supernovas in the process. This democratization of discovery highlights a profound truth about astronomy. The universe doesn't care about credentials. Whether you're a PhD astrophysicist or a high school student with a borrowed telescope, that sudden bright speck in a galaxy's spiral arm could be your ticket to rewriting cosmic history. Every time an amateur reports a potential supernova, they're not just chasing personal glory. They're joining a centuries-old tradition of backyard explorers who have expanded humanity's view of the cosmos one observation at a time. Imagine if every light bulb in the universe burned with identical brightness. You could instantly tell how far away each one was just by how dim it appeared. That's the cosmic shortcut Type Ia supernovas give astronomers. These stellar explosions are nature's most reliable light bulbs, shining with such predictable brilliance that they've become the gold standard for measuring the vast distances between galaxies. The secret lies in their unique origin story. Unlike the chaotic deaths of massive stars, Type Ia supernovas occur when a dense white dwarf, the Earth-sized remnant of a Sun-like star, steals matter from a companion until it hits a critical mass threshold. At precisely 1.4 times the Sun's mass, the entire white dwarf detonates in a thermonuclear fireball so uniform that these explosions consistently peak at around 5 billion times the Sun's brightness. This consistency transforms them into what astronomers call standard candles, objects with known intrinsic brightness that allow scientists to calculate distance based on how faint they appear from Earth. It's like knowing a car's headlight strength and using its apparent dimness to judge how far down the road it is. When astronomers observe a Type Ia supernova in a distant galaxy, they measure its apparent brightness, compare it to the known standard, and bingo, they've got the galaxy's distance. This method works so well that it can pinpoint objects billions of light-years away with less than 10% error, a staggering precision for cosmic measurements. But why are Type Ias so consistent when other supernovas vary wildly? The answer lies in the physics of their detonation. The white dwarf's carbon-oxygen core ignites under nearly identical conditions every time, triggering a runaway fusion reaction that incinerates the entire star within seconds. Unlike core collapse supernovas, where the progenitor star's mass and rotation introduce variability, Type Ia explosions always start from the same tipping point, that magic 1.4 solar masses where electron degeneracy pressure can no longer support the star. It's the cosmic equivalent of a carefully calibrated bomb, guaranteed to explode with the same yield every single time. This reliability has made Type Ia supernovas indispensable tools for mapping the universe's expansion. In the late 1990s, observations of these explosions at extreme distances revealed they were fainter than expected, proving the universe wasn't just expanding, it was accelerating. That Nobel Prize-winning discovery hinged entirely on the trust astronomers could place in these standard candles. Without their predictable brightness, we might still believe gravity was slowly putting the brakes on cosmic growth rather than dark energy flooring the accelerator. Yet even these cosmic yardsticks aren't perfect. Recent studies suggest subtle variations in Type Ia explosions based on their host galaxy's chemical composition or the white dwarf spin rate. Some appear slightly brighter in younger, metal-rich galaxies, while others in ancient stellar neighborhoods might peak a fraction dimmer. Modern astronomy accounts for these nuances by cross-referencing supernova data with host galaxy characteristics, fine-tuning distance measurements like a watchmaker adjusting for temperature changes in a precision timepiece. The next generation of telescopes will push this technique further than ever before. When the Vera C. Rubin Observatory begins its 10-year legacy survey of space and time, it's expected to discover over 20,000 Type Ia supernovas, many from the universe's first few billion years. Each one will add another day to point to our three-dimensional map of cosmic expansion, helping unravel dark energy's mysteries. These dying stars don't just light up the cosmos, they illuminate the very framework of spacetime itself, giving us the ruler we need to measure existence on the grandest scales. Among the countless stellar explosions astronomers have catalogued, one stands out not for its distance but for its raw, staggering power. In 2015, telescopes spotted a supernova so energetic it defied classification, Assassin 15 LH. This cosmic detonation, located in a galaxy about 3.8 billion light-years away, outshone our entire Milky Way by a factor of 20 at its peak. While ancient supernovas like SN UDS10Wil offer windows into the early universe, Assassin 15 LH represents a modern mystery, blasting enough energy in months to power our Sun for 90 billion years. At first glance, this explosion resembled a typical supernova, a brilliant point of light flaring in a distant galaxy. But as observations accumulated, anomalies emerged. Most supernovas fade after a few weeks. This one kept burning brighter for months, requiring an energy source beyond standard stellar collapse models. When scientists calculated its total output around 2 times 10 to the 52 ergs, it became clear this wasn't just another dying star. Assassin 15 LH released more energy in 1 second than our Sun will over its entire 10 billion year lifespan, making it the most powerful supernova ever recorded. What makes this explosion particularly baffling is how it challenges our understanding of stellar physics. Typical supernovas derive their energy from either core collapse or runaway nuclear fusion, but neither mechanism explains Assassin 15 LH's sustained brilliance. One leading theory suggests a magnetar, a rapidly spinning neutron star with an ultra-strong magnetic field formed at the explosion's heart, injecting extra energy into the expanding debris. Another possibility involves a black hole accreting massive amounts of material, though no known process matches the observed light curve perfectly. Some astronomers even speculate this might represent an entirely new class of hyper-energetic stellar deaths, perhaps involving stars hundreds of times more massive than our Sun. Comparing Assassin 15 LH to the distant supernovas we've discussed reveals fascinating contrasts. Ancient supernovas like those from population 3 stars were likely more energetic on average, but their light has been stretched and dimmed by billions of years of cosmic expansion. Assassin 15 LH's relative proximity lets us study its light in detail, catching spectral fingerprints that will be lost in higher redshift explosions. Yet despite their differences, both extremes push the boundaries of stellar astrophysics, proving that even after centuries of observation, the universe still holds surprises in how stars live and die. Perhaps the most humbling lesson from Assassin 15 LH is how much we still don't know about stellar cataclysms. While Type Ia supernovas serve as reliable cosmic yardsticks and core collapse explosions reveal how stars distribute heavy elements, outliers like this remind us that the universe doesn't always follow our textbooks. Every record-breaking supernova forces us to reconsider our models, proving that the cosmos' capacity for violence and creativity far exceeds our imagination. As new surveys scan the skies with ever greater sensitivity, who knows what other luminous monsters might be lurking, waiting to rewrite the rules once again. Interstellar dust might seem like a minor nuisance, but for astronomers hunting distant supernovas, it's like trying to spot a firefly through a sandstorm. These microscopic grains of carbon and silicate, many no larger than a wavelength of light, float between stars, absorbing and scattering the very photons astronomers rely on to study cosmic explosions. The effect is particularly brutal for ancient supernovas whose light must travel through billions of light years of dusty galactic crossroads before reaching our telescopes. What starts as a brilliant stellar death can arrive as a dim, reddened smudge, its original colors and details lost to the cosmos equivalent of fogged-up glasses. The challenge isn't just about dimness, it's about distortion. Dust doesn't just block light uniformly, it scatters shorter wavelengths more aggressively, making distant supernovas appear unnaturally red. This phenomenon, called dust extinction, can mimic the redshift caused by cosmic expansion, fooling algorithms into misjudging distances. A supernova that should appear blue-white might register as deep crimson, skewing measurements of its energy and type. Early observations of some extremely distant supernovas initially classified them as peculiar, low-energy events until astronomers realized they were actually standard explosions obscured by thick dust lanes in their host galaxies. To peel back these cosmic veils, astronomers deploy a toolkit of ingenious techniques. One approach involves studying multiple wavelengths simultaneously. Since dust affects ultraviolet light more than infrared, comparing a supernova's brightness across different parts of the spectrum reveals how much light has been absorbed. It's like determining how smoky a room is by comparing how well you can see a flashlight's beam versus its heat signature. The James Webb Space Telescope excels here, its infrared vision piercing dust clouds that would completely hide a supernova's visible light. Another method exploits polarization, the orientation of light waves after they bounce off dust particles. By analyzing how dust scrambles the light's original polarization, scientists can mathematically subtract the dust's effect, much like noise-canceling headphones isolate a voice from background static. This technique helped correct observations of supernova 2014J, revealing it was a normal Type Ia explosion despite initially appearing anomalously dim. Perhaps the most creative solution involves using dust itself as a measuring stick. Certain types of dust grains emit characteristic infrared signatures when heated by a supernova's flash. By monitoring this secondary glow, often lasting years after the visible light fades, astronomers can calculate how much dust lies between us and the explosion. It's analogous to judging a car's speed by watching how its headlights illuminate roadside signs rather than looking at the car directly. These dust-busting methods don't just rescue obscured supernovas, they unveil hidden chapters of cosmic history. When astronomers corrected for dust interference in observations of ancient supernovas, they found these explosions were more common in the early universe than previously thought. The dust that once frustrated observations became a clue itself, revealing that early galaxies were far dustier than models predicted. likely due to prolific star formation filling them with stellar ash. Every photon that reaches our telescopes from these distant cataclysms has run a gauntlet of cosmic obstacles. By learning to read between the dust particles, we're not just seeing through the fog, we're discovering how the universe sweeps up after its most violent explosions, leaving trails of stardust as breadcrumbs back through time. At the extreme end of cosmic violence, some supernovas don't just explode. They unleash focused beams of annihilation so powerful they can sterilize entire galaxies. These are gamma-ray bursts, or GRBs, the universe's most luminous event since the Big Bang. Lasting anywhere from milliseconds to several minutes, a single GRB can outshine every star in the observable universe combined, but only if you're directly in its crosshairs. What makes these phenomena so terrifyingly unique isn't just their energy. It's how they're born from a very specific, catastrophic breed of supernova. The deadliest partnership in cosmology begins when a rapidly rotating, massive star, typically 30 to 50 times the Sun's mass, collapses at the end of its life. Unlike a standard core collapse supernova, where the star's outer layers rebound symmetrically, these progenitor stars channel their fury into narrow jets moving at 99.99% the speed of light. The physics behind this is like turning a garden hose into a fire hose by pinching the nozzle. As the star's core collapses into a black hole, intense magnetic fields and rapid rotation focus the energy into twin beams erupting from the poles. The rest of the star, it gets obliterated in the shockwave, but not before the jets punch through its surface, accelerating particles to energies even our most powerful particle colliders can't match. These jets are where gamma-ray bursts come to life. As they plow through interstellar space, internal collisions within the jet generate gamma rays, the most energetic form of light, through processes we're still unraveling. Some theories suggest synchrotron radiation, where electrons spiral around magnetic field lines at relativistic speeds, while others point to inverse Compton scattering, where low-energy photons get boosted to gamma-ray status by high-speed electrons. The result is a pulse of radiation so intense it can ionize atmospheres on planets thousands of light-years away. Evidence suggests a GRB hitting Earth 450 million years ago may have triggered the Ordovician extinction, stripping the ozone layer and devastating marine life. But here's where supernovas enter the picture. Not all GRBs are created equal. The longest bursts, those lasting over 2 seconds, are almost always linked to a supernova weeks later. Astronomers call these collapsars, and they follow a grimly poetic sequence. First the gamma-ray blast, then the fading afterglow in X-rays and visible light, and finally, the emergence of a supernova's characteristic light curve as the stellar debris expands. The smoking gun came in 2003, when the afterglow of GRB030THREE Chinese letter revealed a supernova lurking beneath, its spectrum rich with newly forged heavy elements. This confirmed what theorists had long suspected, that at least some GRBs are supernovas in disguise, their energy funneled into beams rather than spherical explosions. What makes these hybrid events so rare? It's all about stellar pedigree. The progenitor star needs extreme characteristics, rapid rotation to twist magnetic fields into focused jets, low metallicity to prevent stellar winds from sapping its angular momentum, and enough mass to form a black hole instantly. Stars meeting these criteria might account for less than 1 in 10,000 supernovas, which explains why we've only spotted about 24 GRB supernova pairs despite monitoring the skies for decades. When conditions align, however, the results redefine our understanding of stellar death. The famous GRB 980FOUR Chinese letter, for instance, produced a supernova SN 1998BW that was 10 times brighter than a typical core collapse event, its light curves suggesting unprecedented nickel-56 production. For astronomers, these explosions are cosmic Rosetta Stones, offering clues to phenomena ranging from black hole formation to the origins of heavy elements. The same jets thought to power GRBS might also explain hypernovas. Supernovas 10 to 100 times more energetic than normal. Some researchers speculate that neutron star mergers another GRB source couldn't produce all the universe's heavy elements without help from collapsars. Even the gravitational waves detected from such events carry imprints of the progenitor's rotation, a fingerprint of the conditions needed to launch these relativistic jets. Yet for all their destructive potential, GRBS and their supernova siblings play a paradoxical role in the cosmos. The same radiation that could end life on nearby planets also propagates elements essential for life across interstellar space. Their beams, detectable across billions of light-years, serve as nature's ultimate lighthouses, helping astronomers probe the early universe's star formation rates and chemical evolution. And perhaps most remarkably, they remind us that even in death, stars can transform into something far more extraordinary. Not just explosions, but cosmic accelerators pushing the limits of physics itself. Here's a cosmic quirk that bends the mind when we observe a distant supernova's light curve. We're not just seeing light stretched across space, but time itself stretched thin. The universe's relentless expansion doesn't merely redshift photons. It slows down the very appearance of the explosion, turning what should be a swift stellar death into a drawn-out cosmic ballet. Imagine watching a fireworks display in slow motion, where each burst lingers far longer than it should, except in this case, the firework is a dying star halfway across the observable universe, and the slow motion effect isn't an illusion, but a fundamental distortion of space-time. This phenomenon, called cosmological time dilation, occurs because the expanding universe stretches not just the light's wavelength, but the intervals between emitted photons. A supernova's light curve, the rise and fall of its brightness over days or weeks, gets smeared across a longer observed duration the farther away the explosion is. A supernova that brightens and fades in 20 days locally might appear to unfold over 40 days at redshift 1 or 80 days at redshift 2, with each doubling of distance stretching time like taffy. It's as if the universe itself hits a cosmic pause button on distant events, forcing astronomers to account for this temporal warping when comparing explosions across cosmic epochs. The evidence for this effect is etched into the light curves of Type Ia supernovas. These standardizable candles have remarkably consistent peak brightness and decay rates, but only after correcting for time dilation. In 2208, astronomers analyzing distant supernovas found their light curves progressed exactly as predicted by Einstein's theory. A supernova at redshift 0.5 unfolded 1.5 times slower than nearby counterparts, while one at redshift 1 progressed twice as slowly. This wasn't just confirmation of cosmic expansion. It was proof that time itself flows differently across the vast gulf between galaxies. But here's where it gets even stranger. This time dilation isn't uniform across all wavelengths. Higher energy photons like ultraviolet get stretched more dramatically than lower energy ones like infrared, creating a bizarre observational effect where different colors of the explosion appear to fade at different rates. It's like watching a rainbow unravel, with each hue lingering for its own distinct interval. Modern telescopes like JWST must account for this chromatic time warping when analyzing ancient supernovas, reconstructing their true light curves by stitching together multi-wavelength observations like pieces of a temporal puzzle. The implications ripple far beyond supernovas. Time dilation means the early universe's most violent events, quasar flares, gamma-ray bursts, even the formation of the first black holes, might appear to us as languid, drawn-out processes despite occurring at breakneck speed in their own reference frames. A black hole merger that took milliseconds in reality could appear to unfold over hours when observed from 13 billion light-years away. This cosmic sleight of hand reminds us that the universe isn't just a vast space to explore, it's a vast time to unravel, where the very pace of events depends on where you stand in the grand, expanding tapestry of existence. Among the countless stellar explosions lighting up the cosmos, a rare breed stands apart: superluminous supernovas, shining 10 to 100 times brighter than their ordinary counterparts. These cosmic anomalies don't just push the boundaries of stellar physics, they shatter them, radiating more energy in months than our Sun will over its entire lifetime. While typical supernovas fade after weeks, superluminous events can blaze for years, their light curves lingering like cosmic afterimages. What makes these explosions so extraordinary isn't just their brilliance, it's how they force us to rewrite the rules of stellar death. At the heart of the mystery is their power source. Ordinary supernovas draw energy from collapsing cores or runaway fusion, but neither explains the staggering output of these stellar behemoths. One leading theory points to Magnetar's newborn neutron stars spinning at dizzying speeds, their immense magnetic fields injecting extra energy into the expanding debris like a cosmic turbine. Another hypothesis involves pair instability explosions, where stars so massive their cores become furnaces for matter-antimatter pairs, triggering total annihilation. Then there's the circumstellar shell model, where the explosion slams into previously ejected material, converting kinetic energy into blinding radiation. Each scenario paints a different portrait of stellar demise, yet none fully account for the diversity of superluminous events we've observed. The connection to ancient supernovas adds another layer of intrigue. Some of the most distant explosions ever detected bear striking resemblances to nearby superluminous events, suggesting these extreme phenomena might have been more common in the early universe. Back then, stars were often bigger, purer in composition, and prone to violent deaths that today's metal-rich galaxies rarely produce. Superluminous supernovas could be fleeting glimpses into that primordial era, local echoes of the universe's fiery youth. What makes these cosmic oddities truly transformative is how they challenge our understanding of element formation. Their prolonged brightness often signals copious production of radioactive nickel, the decay of which powers their long-lasting glow. But some exhibit strange chemical fingerprints, hinting at exotic nuclear processes we've yet to decipher. Each new discovery peels back another layer, revealing how stars can die in ways we never imagined, and how much we still have to learn about the universe's most dazzling finales. The most exciting thing about distant supernovas isn't what we've already discovered, it's what lies just beyond the edge of our current understanding. With telescopes growing more powerful by the decade, future observations could crack open cosmic mysteries we can't even imagine today. Picture this: a supernova so ancient its light predates the formation of galaxies as we know them, revealing how the first stars lived and died in the universe's chaotic infancy. Or an explosion that defies all known physics, shining with unfamiliar spectral lines that hint at undiscovered elements or exotic states of matter. These aren't science fiction scenarios, they're realistic possibilities waiting in the data streams of next-generation observatories. One frontier is dark matter's shadowy influence on stellar deaths. Current models assume this invisible substance only interacts gravitationally, but what if certain supernovas show anomalies in their light curves or elemental ejecta that suggest otherwise? A distant explosion's debris expanding slightly slower than expected, or strange asymmetries in its remnant, might betray dark matter particles colliding with stellar material, evidence that could finally unravel this cosmic riddle. Similarly, subtle variations in how ancient supernovas redshift could test whether dark energy's strength has changed over time, challenging our assumptions about the universe's ultimate fate. Then there's the potential for entirely new classes of stellar explosions. The history of astronomy shows that every time we build better telescopes, we discover phenomena previously deemed impossible. Hypernova, pair instability supernovas, and magnetar-powered bursts were all theoretical until observations caught up. Future surveys might uncover ultra-long-duration supernovas fueled by black hole accretion, or failed explosions where stars collapse directly into black holes with barely a whimper. Some theorists even speculate about quark nova, stellar remnants so dense they crush neutrons into free quark matter, releasing bursts of strange radiation that would rewrite nuclear physics textbooks. The James Webb Space Telescope and its successors will peer deeper into the infrared than ever before, potentially spotting supernovas from the universe's first few 100 million years, the era of population Roman III stars. These primordial explosions could show chemical signatures unlike anything seen today, forged in conditions so extreme they no longer exist. Imagine detecting a supernova devoid of iron but rich in unusual isotopes, proving that the earliest stars operated on different nuclear pathways. Or finding evidence that some massive primordial stars collapsed directly into black holes without exploding at all, leaving behind cosmic dark births visible only through gravitational lensing. Perhaps the most revolutionary possibility is discovering that supernovas aren't always what they seem. Certain theoretical models suggest that phenomena like cosmic strings, defects in spacetime from the early universe, or colliding higher dimensional branes in string theory could mimic supernova light curves while originating from entirely different processes. A bizarre, unexplained explosion at the edge of the observable universe might turn out to be our first glimpse of physics operating at energies trillions of times higher than any particle collider can reach. The coming decades will transform supernovas from mere celestial events into precision tools for probing fundamental physics. Future arrays of gravitational wave detectors could sense the space-time ripples from a supernova's collapsing core milliseconds before light arrives, giving unprecedented views into the explosion's hidden initial stages. Neutrino observatories might catch particles bearing quantum information about conditions deep inside the implosion, impossible to glean from light alone. And with machine learning sifting through petabytes of telescope data in real time, we could catch these cosmic fireworks at their very inception, watching the first instance of stellar death unfold across wavelengths from radio to gamma rays. What makes these possibilities so thrilling is their unpredictability. Every major leap in telescopic power has revealed cosmic phenomena that theorists never anticipated, from accelerating expansion to dark energy. The supernovas of tomorrow won't just answer today's questions. They'll pose entirely new ones, sending astronomers back to their chalkboards to rethink the laws governing stars, elements, and spacetime itself. Each flash from the distant cosmos carries the potential to rewrite our understanding of reality, reminding us that the universe's greatest revelations often come wrapped in the brilliant demise of its most massive stars. From the ashes of dying stars to the farthest edges of the observable universe, we've journeyed through 30 astonishing facts that reveal how supernovas aren't just cosmic fireworks. They're the universe's storytellers, chemists, and architects. These distant explosions light up more than just the void. They illuminate the deepest questions about time, matter, and the very fabric of reality. Think about it, every atom in your body, the expansion rate of the cosmos, even the mysterious force we call dark energy, all these trace back to the life and death of stars so far away their light has traveled longer than Earth has existed. One of the most humbling realizations is how supernovas serve as time machines. The light from explosions like SN UDS10Wil didn't just cross space, it bridged epochs, carrying snapshots of a younger, hotter universe where galaxies were still taking shape. These ancient bursts help us measure cosmic expansion with precision, proving the universe isn't just growing but accelerating, driven by dark energy's invisible push. And let's not forget their role as cosmic alchemists. Without supernovas scattering heavy elements across space, planets like Earth and life itself wouldn't exist. The iron in your blood, the gold in your jewelry, even the device you're watching this on, all were forged in stellar explosions billions of years ago. Yet for all we've learned, these distant supernovas keep reminding us how much remains unknown. Why does dark energy dominate the cosmos? Could some of the universe's first stars still linger in the void? What bizarre physics might we uncover in the next record-breaking explosion? The beauty of astronomy lies in these unanswered questions, the mysteries that keep us looking up and wondering. So here's your call to action. The next time you step outside on a clear night, take a moment to gaze at the stars not just as points of light, but as distant suns with stories yet to be told. Some of them may have already died in spectacular supernovas, their light still racing toward us across the ages. Others could be ticking time bombs, waiting to rewrite our understanding of the cosmos in a flash of brilliance. The universe is vast, strange, and full of wonders, and every discovery starts with a single spark of curiosity. Keep looking up, keep asking questions, and remember, we're all made of stardust connected to these distant explosions in ways we're only beginning to comprehend.